Okay, let's go ahead and hook up this peptide. That's the name for amino acid chains, peptide chains. And once it gets long enough to actually have function, then we'll call it a protein. So in this case, it's a tripeptide for obvious reasons. There's 3 of them. You'll probably want to set it up initially to look like something like this. Oops. All right, I'm gonna give myself some more space. Are we okay with that so far?
Except for your seeds, you even need another
Where?
the first and
Oh,
third.
oops. It's all right. I'm sorry, so we're talking about,
Those guys, do they need another?
those guys?
Yeah.
Do they need another H? Why don't I have anything in those spots? Why are there only 3 bonds? Those are the side chains that identify it as A, W, and T. So that's the position. In my first one here, I'm gonna go ahead and just write a CH3 group. Because A stands for what? Alanine, which is amino acid that's got us a methyl group in that alpha amino acid position. The next one's a W. It's a little bit more complicated. Tryptophane, and we talked a little bit about tryptophane last time, right? That's too many. What did we talk about last time with the tryptophane? Yeah, it's an amino acid that it's a little higher concentration of tryptophan in turkey than anything else. So for a long time, people thought tryptophan was what was making people sleepy during turkey dinner, but it's just a massive amount of food. And threonine is the T. And so that's what your structure should look like. Looking at this kind of structure, let's say instead of this just being 3 individual or 3 amino acids in a sequence, let's say this is 3 amino acids in a much longer sequence. And on the other side over here, there was another set of peptides. What kind of peptide would this most likely interact with? What would I want to put right here? Possibly, or another one opposite, depending on what the situation is. So I have a nitrogen group right there, right? So if I put an acid, I could add an H to that nitrogen, and then that would put a positive charge on that nitrogen and a negative on the acid, and then those 2 things would have a salt bridge amongst them. This CH3 group here is nonpolar, right? So what if I put another nonpolar substance like proline? Or isoleucine, then those 2 guys would be attracted to each other. And then the same situation over here, if I had something that was polar, the hydroxyl group would be attracted to, so an acid or a base or another polar substance, then I would want that to be here so they could be attracted to each other. What type of bond cause amino acids to bond to each other, and what's the name of the bond?
Peptide bond.
All right, so it's a peptide bond. And what's the impetus? That's a dehydration reaction, right? So again, if nature can make water, nature won't make water. And so what we're seeing, if we scroll back up to this, is what is missing. Oh, that's huge. What's missing right here? There's an OH group that should be there, and also on the nitrogen, what should be there? Another H. So the water molecule left because an H left the amino side and an OH left the carboxylic acid side. Description for the primary structure? What do we got? Does this primary structure have any functionality? So on that list of things that we talked about that proteins can do, can a primary structure do any of those things? Nope. Cannot do any of those things. This is more like the building blocks before the building gets put together. All right, how about the secondary structure? We have three types of secondary structures, and it's important that we note how the secondary structure actually is formed, and what is it about the interaction within the protein that allows a secondary structure formation. How about this? When a secondary structure forms, what components in this protein are binding to each other? Not the side chains, the backbone. And when we say backbone, we're talking about the We're talking about this portion of the molecule only. So this section of the molecule is going to interact with another section of a protein, but only that part. So specifically we're saying, say, this N right here will chemically have a hydrogen bond with a hydrogen someplace else further down on the molecule. But this hydrogen bond that this nitrogen forms has nothing to do with any of the side chains. So if I get an interaction, the interaction is going to be further down on the chain to someplace else in the backbone, which is why these structures have what kind of formation? What would you say about them? Regular. They're symmetrical and regular, as opposed to the way the rest of the protein looks, which basically looks like somebody took an extension cord out and then just unwound it and then just threw it on the ground. Even though that looks very chaotic, it's very specific, but the portions of that are secondary structure are very, very regular, not chaotic in any way, shape, or form. How is it that an amino acid can act or behave like a buffer? What is it about it that allows it to do that? It's got an acid and it's got a base. If we talk about it in this format, I can have that H pop off if what happens? If an OH was added to the solution, if there was excess OH, that H would pop off and neutralize that hydroxyl group. Or that nitrogen right there. If an H plus, or there was excess H plus added to the solution, that two lone pairs of electrons on the nitrogen group would absorb that H plus, thereby again taking it out of the solution. So if I increase the H plus, pH would drop, but then if it was again taken out of the solution, then the pH goes back up to where it was before. And this last question about amino acid separation, what do we do here? Electrical current? We actually don't have any electrical current flow. We just produce an electrical potential. I'm going to draw it sideways. So I have a piece of equipment that we call gel electrophoresis, and I apply a voltage to it. Current isn't actually allowed to transfer across it. It's just over here there'll be some sort of positive voltage, maybe 200 volts. On the other side I'll have negative 200 volts worth of electricity. So basically I've got a battery that's got a 200 volt battery, and I take the wires and I connect them to the machine. So it would just be the same like if you took your took a 9 volt battery and put it on your tongue and you felt that. The same thing would happen if you were to touch these leads. But these leads aren't in a contact with each other that would allow them to transfer electrons. So the electricity doesn't flow. So if in the solution I have a particular amino acid, okay, so there's just some random amino acid in its non-Zwitter format, and if I turned an electric field on, where would this molecule go? It would go nowhere. It doesn't have a charge, so it would go nowhere. So what I could do is, what would happen if I dropped the pH of the solution? So the pH of the solution was, I don't know, 5. I'd have excess H pluses floating around. And what would those excess H pluses do? They would attach to that nitrogen right now. And now this molecule has what kind of charge? It's got a positive charge, right? So now if I turn on the electric field, what's going to happen? It's going to move this way, right? So if I've got a bunch of amino acids in there, what I can do is set a pH relative to this R value here. And then H's will go on or come off of that R, and the amino acids will either move or they won't move. The other way that this could be done would be when did you guys do chromatography? It was like Chem 104, week 3. Piece of paper, put the dots on there, put it in a solution, they move through. So the way that you would do it with this is a slightly more complicated method. Instead of having a piece of paper, you'd have a long tube, and on the inside of the tube there'd be substances that the amino acids would interact with for a short period of time. You'd have your solution of amino acids, and then you'd let it go through the tube. And you'd have it at a high pressure, so it's shooting them through the tube. But as the amino acids themselves hit the walls, they may or may not interact with the wall. Just like those 3 dots may or may not have moved up that piece of paper very easily. So the iron one moved all the way to the top of the piece of paper because it did not like the paper, and it really liked the mobile phase. And that's the same situation we have with liquid chromatography. The liquid is the mobile phase, and the tube is the stationary phase, and these amino acids would interact or they wouldn't interact with the tube depending on what kind of stuff you got inside. And that way literally you just slow them down. And so they all come out of the tube, but initially only the one that likes the liquid the most comes out of the tube. And then that's amino acid number 1. And then amino acid number 2 comes out the next fastest until you get amino acid number 20 that comes out the last, because it really liked the walls of the tube. So it was slowly moving its way through the tube, as opposed to the first one that came flying out because it didn't like the tube at all. So, go ahead.
That would like just relate to like its polarity.
It could be polarity. So if you wanted the solution to come, if you wanted aniline to come out of this liquid chromatography tube very quickly, the inside wall of the tube would be polar, because aniline is nonpolar. So every time it hit the interior of the wall, it would just bounce off of it and try to get the heck away from it and stay in the liquid and just travel through. Where the polar molecules, like the threonine, has a alcohol group on it. It sees a polar substance on the wall, it just grabs a hold of it and holds on for a little while, and thereby the alanine is already way down the tube ahead of it, because it every time, I mean, it's stopping to smell the roses. It sees something that it likes and it waits for a little while. It's like a dog on a well-peed street. Wants to smell every single thing, every tree, every bush, every fire hydrant, every corner. So that's basically what you do. You put things in there that would be attracted to that amino acid, and then the other amino acids aren't attracted to it, so they just come flying out the tube. And literally, the dog who has a bad sense of smell gets to the end of the block first, and the dog with a really good sense of smell is lingering. Do we have any questions about that?